Okay, everybody, today we're going to be using Circuit 7 from the SparkFun Inventors Kit, which is the temperature sensor circuit, to explore how we use calibration to get the most accurate data that we can and to get data that has a certain dimension value that we need. In the case of temperature, we're thinking in terms of Fahrenheit and degrees. So go ahead, if you haven't already done so, and build Circuit 7 on your board right now using the temperature sensor that is included in your kit, and you'll have one side wire going to 5 volts, the other side wire goes to ground, and then the middle pin goes to analog 0. This is once again another analog to digital conversion using the analog read, which splits up the 0 to 5 volts that Arduino is capable of taking into 0 to 123. Then that value, which is essentially dimensionless in terms of temperature, is converted to a voltage value and then ultimately to Fahrenheit and Celsius. Okay, let's take a look at the sketch for Circuit 7 real quick. Go ahead and open that up. It's Sketch 7 that goes with the SparkFun Inventors Kit guide of sketches. And as you scroll down, there's some introductory text, and then we come to our initializing, where we declare temperature pin analog 0 is constant in. You could use in if you wished. And then we go to void setup, open those brackets. We are going to want to look at the serial port, serial begin 9600, and then we get to the loop stage, and we start off with declaring floats. Now, as I've mentioned before, a float value is any value that has a decimal point. And for us to get any real accuracy in temperature, we're going to have to use floats. And so it's declared that our voltage value, our degrees Celsius value, and our degrees Fahrenheit value will all be floats. So we can be getting tenths or even 1/100ths of a degree. And then we go to working out our algorithm for voltage. Voltage equals get voltage temperature pin, and we come up with our algorithm for finding degrees Celsius. That is voltage minus 0.5 times 100 will give us degrees Celsius, and then degrees Fahrenheit is found by taking Celsius and doing the basic Celsius to Fahrenheit conversion, multiplying it times 9/5 plus 32. From there, we do our serial prints, and in this case, there's printing of voltage, degrees Celsius, and degrees Fahrenheit. So we actually tell it to print the header for each one, voltage, and any text that you put in the serial monitor, it needs to be in quotation marks. And so we have voltage, and then there's the space to represent the number that will be put there. Then degrees Celsius, same way, and then degrees Fahrenheit. Okay. After we've set our degrees, I've reset the delay for 5 seconds, 5,000 rather than the 1,000 to slow things down. And to wrap up the sketch, we have basically the turning of our int value, which is our analog read value, into our float get voltage, and then at the end we have a term that we haven't encountered before called return, and what that does is allows us to convert that 10 to 123 back into voltage using this conversion factor. Alright, so let's click on the serial monitor and see what's happening with the temperature. And so it's printing the three values that are in the sketch: voltage, degrees Celsius, and degrees Fahrenheit. The voltage is 0.72. The degrees Celsius is coming in at about 22.27, and Fahrenheit 72.08. Now, we decided that we might want to compare this sensor with a very stable, high quality thermometer, such as the vernier digital probe that we're going to be using for our project. And I've got one hooked up and a Logger Pro display here, so we can compare the temperatures that are going on right now. And we see the temperature fluctuating on the vernier probe around 25.2, and whereas the temperature sensor on the Arduino is sort of fluctuating between 22.27 and 22.75. So that is a bit of a difference in the temperature. We are going to assume that the stainless steel probe of the vernier is closer to the true value, and that means that we may want to recalibrate the values for the Arduino's temperature sensor, since we assume that it's probably not quite as stable and probably not quite as accurate as the vernier. After all, that little sensor is probably about 75 cents, very susceptible to signal noise and fluctuations, whereas the vernier probe has been designed for higher quality, higher stability, more accurate, more precise readings. So what we'll do is let's work out a new algorithm that will get the value of the temperature sensor closer to the true value. And as I said earlier, calibrating and ultimately recalibrating is what you want to be doing often to make sure that your data in the field is accurate. So this is going to be a good example of that. So let's take a look at how we would go about recalibrating our sensor in the sketch. Now, the current sensor calibration on the Arduino sketch has a line that says degrees C, or degrees Celsius, equals volts minus 0.5 times 100. And the temperature sensor just a second ago was reading most of the time about 22.75, and the vernier probe was reading about 25.1. So our goal here is to find a new conversion factor that replaces the 0.5 value right here with something that is more, that will get the output in Celsius and ultimately Fahrenheit closer to the true temperature. So what we do is let's rearrange the current formula that was up here for the vernier value. We said earlier that the vernier value was 25.1, and the voltage was reading, when it was at the temperatures that we were looking at, the voltage on the screen was 0.73 for the output on the vernier temperature sensor. So what we're going to do is we're going to try to find what our new conversion factor is. The voltage being 0.73 in this particular situation, and we've had 0.5, but we need a new conversion. So let's do a little bit of algebra here and rearrange this formula for the sought after value that the vernier is putting out. We simply move the 100 over here, which makes to the left side of the equal sign, which makes it 0.251, and then the other side, 0.73 minus x, we get 0.73 over the other side by subtracting it into the amount on the left hand side of the equal sign, just like in algebra 1, and we get 0.479 equals negative x. We can cancel those negatives and round to about 0.48, and we'll let that be our new conversion factor. That, of course, is pretty close to 0.50, but by reducing it just a bit, we hope that it'll actually bump up the temperature that the sensor is putting out, so it'll be closer to the probe. So our new conversion factor in the sketch will be changed to degrees C equals V minus 0.48 times 100. So why don't we do that? Okay, so what we did was we took our new formula here for degrees Celsius from voltage, and we changed that 0.50 to 0.48, and we're hoping what that will do is get the temperature sensor's output a little more in line with the verniers, which is a more expensive, high quality thermometer that gives a more accurate reading. So let's take a look on the serial monitor and see what we're getting right now. And it shows that we are getting a good deal closer here. Now the temperature on Logger Pro is now about 25.2. The temperature on the sensor is bouncing between 24.75, 24.27. And so it's not perfect, but it is getting it, at least about a degree and closer pretty consistently, sometimes even closer than that. So at any rate, the whole idea about calibrating is that you are trying to make sure that your data is as accurate as possible. And that means by making sure that your instruments that you measure are accurate as possible. All of our sensors that we're using, all the water sensors, all of the air sensors have to be calibrated at some point. Some are very stable, like the temperature sensors, and you may not have to at all, at least this fall. Whereas when we go out in the field, the water quality sensors like pH need to be recalibrated, and our air quality sensors are going to be definitely have some tricks about them that we're going to work through to get those to not just put out an analog value, but to put out a value that reflects something that we really can measure, such as parts per million. But at any rate, hopefully that gave you at least an idea of sometimes how you have to use a little math to make sure that your data has some meaningful accuracy.